Welcome to PostNetwork Academy, where we make complex topics in mathematics, AI, robotics, and data science crystal clear. I am Bindeshwar, and in today's lecture, we are diving deep into one of the foundational concepts in linear algebra vectors and vector spaces. So, whether you are a student preparing for exams, a data scientist, you are math lover, or beginner in machine learning, understanding vector spaces is absolutely essential. They are not just abstract math, they power everything from recommendation systems to deep learning and robotics. So, without further delay, let's get started. So, let us understand Rn Euclidean space. So, the set of all n tuples of real numbers is denoted by Rn, and here you can say that a vector having elements from Rn. These elements from R, and that is a vector space belong to Rn, and each u is called a point or vector, and the components ai are called either coordinates, components, entries, or elements, or even scalar. So the term scalar is used for an element of R. So that means scalar, so that belongs to R. Now let us understand equality of vectors and also zero vector. So two vectors u and v are equal if u is equal to v if there is a condition like they have the same number of components and corresponding components are equal. Here you can see that they have same number of components and even they have the same numbers but position are different, so they are not equal. Also the zero vector, that vector is called zero vector, that is also denoted by zero, or sometimes you will see that zero hat. These are zero vectors. So see the example, these two vectors, these are in R square, and here zero vector in R cube, and here also another vector in R cube. So these are examples of vectors. Now let us understand vector space, a very important topic in linear algebra, and that powers artificial intelligence, machine learning, deep learning algorithms, and in generative AI like transformers and others generative AI architectures. So that is very important. So if V be a non-empty set with two operations, these operations are, see, the addition, vector addition, and scalar multiplication. So vector addition means you are adding two vectors that belongs to V, and if U belongs to V and K belongs to K, that means a scalar. So that product will belong to vector. Then V is a vector space over field K if it holds for all vectors U, V, and W. So there are 8 axioms that must be satisfied. So A1 means addition axiom. U plus V, that is associative law. There exists a zero vector such that U plus 0 vector is equal to 0 plus U vector, that is means commutative. And here there exists an opposite element negative, you can say that negative element, that means if you add, so that would be equal to 0. Inverse, you can say that additive inverse, E3 is an additive inverse, and that is commutative. That means u plus v is equal to v plus u. Again, let us see in multiplication. So k, that means scalar k can be distributed over vectors. Here, that means ku, kv. That is a multiplication axiom. So that is first multiplication axiom. You can see that m1. Thereafter m2. That means sum of scalars will be distributed over vector. Let us see the third one, a bu, that means associative. Let us see the fourth one. If you multiply a vector by unit, so that would be again the same. Unit is scalar here, not vector. So the additive structure forms a commutative group. Vector sum, that is associative. Zero vector is unique, and each vector has a unique negative. That means there is only one zero vector, and each vector has inverse, additive inverse or additive inverse, that is negative. That is negative and unique. U plus v, w is equal to v. Then that would be equal. That means if u plus w and v plus w, that will get cancelled. Cancellation also holds. Subtraction. Let us see some example of vector spaces. So vector space Kn. So K be a field, then Kn is the set of all n tuples of elements in K. So vector addition holds, because if you take this one vector and second vector, so addition will be another vector. Multiplication, so scalar, if you multiply a scalar C with vector, so you will get this one. Zero vector holds, and negative vector. If you have a vector, so there is a negative vector. So that means Kn can be regarded as a vector space over K. Now polynomial space. So let Pf be the set of all polynomials. So also there is vector addition, scalar multiplication, there exists zero polynomial. So Pf is a vector space over F. So these three properties should hold. So that would be a vector space. So polynomial space, subspace, the same. So it must be, I am talking about subspace. So is a subspace of Pf if closed under addition and scalar multiplication. Two properties should hold. Matrix subspace. So let M n F be the set of M cross n matrices over field F. Then matrix addition and scalar multiplication defined element wise, and that forms a vector space over F. Function space. So here you can say that here vector addition and scalar multiplication both hold. So Fx is a vector space over F, and we will see in detail about these vector spaces with examples and applications. So hope you understood what is a vector and vector spaces in linear algebra. For more resources, you can visit www.postnetwork.co. YouTube channel you can visit, Facebook page, and you can also visit my PostNetwork Academy LinkedIn page. Also, you can visit GitHub repositories for projects, and also some other projects and code repositories. So hope you understood. Thanks for watching the video.